So this is problem 3.8, number 37. Effectively, you want to show that, I guess the statement of the problem, I didn't write it on my paper, but it must be that multiplication of matrices is associative in the world of Boolean matrices. There's different notation for sum and product with Boolean. Bear in mind that that's only a difference in notation. I'm just going to use ordinary notation and show you how to go back and change it to some other notation. This is, by the way, the kind of problem that gives math a bad name, in my opinion. It's a horrible, messy bookkeeping, and that's about it. But I guess that's what makes it somewhat confusing. So the idea is that you've got this product, A times B times C in Boolean world, and you've also got the opposite association you might consider, which is A times B times C associated that way, and you'd like to say that those are equal just like they are for normal arithmetic. And really, the way to prove that is you have to look at, well, what is a typical element of this matrix, and what is a typical element of that matrix? And they each have coordinates, right? And by the way, these matrices are sized in such a way that the products work. So there's a P by Q, Q by R, and R by S, or whatever numbers you choose. They have to line up correctly. And then you want to know what the ikth entry of each of these matrices is, and I'm going to call that I, comma K, and here I, comma K. There'll be some IK entry, and if those are equal entry by entry, pairwise, then they're equal. And so that's really what we want to prove. And by the way, this is to prove, hasn't been proved yet. And it's just basically a calculation. I just want to make sure I get my indexes, choices down the way I have them in my notes here. So let's look at the left-hand side. This product here is a sum. It's always the sum of a row of A and multiplied pairwise with the column of the one on the right-hand side, and that column will be a column of that product. So we're going to write that as a sum, and I'll choose to use J for my summing subscript, and that'll be an entry from the ith row of A, Aij, and then you're going to multiply that by an entry of the jth column of this thing, so that'll be jk, and that's got to be an entry, the jk entry of that product goes right there. And so we have to see what that is and just plug it in. So this is going to be a sum over j times aij times, I'm going to substitute in what the jk entry of this beast is. Well, that's another sum, and I'm going to use L for my sum subscript on that one, so it'll be a sum over L of row times column of B and C. Row would be B, J, L, and column will be C, L, K. And notice that the way these subscripts are lining up here. Just to keep things straight, this J comes from here, this K comes from here, and the L is the thing that is varying during that sum right there. Here, of course, the I and the J, so the J matches up with that J there. So now I want to point out that the sum, arithmetic has this distributive law. So this is a product of an A thing times a sum of some B times C things. And the product of A times B plus C is the same as A times B plus A times C, ramified over all that summing. And so this is just the same as taking the sum over J, multiplying the A inside, leaves us with a sum over L of this times this times this. A I J, B J L, C L K. And again, notice that J and L are the subscripts over which we're summing. And I guess I was circling those, but I'm going to just underline the I and the K to show that they're not changing in this sum. And they're producing, remember, we're looking for the I-K entry in this left-hand side. If we go to the right-hand side, it's a similar kind of problem.
Can we hold on 1 second?
So now we're going to go to the right-hand side and calculate its I-K entry as a sum of the product of three kinds of things. And it's the judicious choice of the variables that you used for the sum is going to help a lot. So we're going to calculate this over here, and I'm going to make that the sum over L of some entry of the product AB, and that'll be the I-L entry times C-L-K. So notice that I and K are not being summed over here. They come from the entry that I'm trying to calculate. And that's the same as this entry here, the same subscripts. So that's the I-K entry of the right-hand side. Now we want to expand this A times B just like before. So we want the I-L entry of that, and I'm going to use J for my summing subscript there. So that will be the sum over J of A I J times B J L and then C L K here. Now, again, the distributive law works from the right as well as the left. So A plus B times C is the same as A times C plus B times C. And so I can rewrite this as a sum over L and then a sum over J. And that'll be over A, I, J, B, J, L, C, L, K. And I, and the K are the surviving subscripts, and the ones that I'm summing over are first L and then J. So now compare that to what I have over here. I sum, well, the inner sum is over L and the outer sum is over J. Here the inner sum is over J and the outer sum is over L. But hey, you're just adding up a blizzard of triple products, and it doesn't really matter what order you add them up in. And so you can interchange L and J here, and it will make no difference on the sum, because the sum is the sum of a bunch of things that is associative and commutative. And so you can rewrite that as the sum over J of A, I, J, B, J, L. Wait a minute, I forgot. Sum over J and then sum over L. A, I, J, B, J, L, C, L, K. And that is identical to this thing we got from the right-hand side. And so because these are identical, they are equal. And so we've shown that the left-hand side equals the right-hand side up here, entry by entry. In other words, IK entry by IK entry. Now, the notation I'm using here is that of ordinary arithmetic, only because that's what we're used to. But just define sum to mean sum in the world of Boolean algebra instead of ordinary algebra, or Boolean arithmetic instead of ordinary arithmetic, and make sure that the rules we applied still hold. The rules we applied are the distributive law. Boolean product distributes over Boolean sum. In other words, Boolean product is the and, the upside down B, and Boolean sum is the right side up B, and we know that distributes, so no problem there. And we know that Boolean sum is commutative, and so that gives us the right to interchange the way we add things up. And those are really the only two laws of arithmetic we used in this. So in any system that has the distributive law and has commutative and associative addition, this will be a true statement. And in particular, it'll hold in the Boolean world.